Hello, welcome back from lunch. My name is Harold. I'm going to help chair this next session, Group 10. We have 4 great speakers lined up for you today. First up is Alexandra Kalinovska, and she's going to talk to us about online user assessment for robot-based assistants. So, as soon as you're ready. Okay,
cool.
Go ahead.
Hi, my name is Alexandra Kalinovska, and I'll be talking about real-time user assessment for robotic interaction. Robots are often used for training or assistance in a specific task. For instance, lower limb exoskeletons in the task of walking. This is me in a commercially available exoskeleton, but imagine a stroke survivor with a weak limb or a paraplegic with no control over their lower body in that same device. How do we provide meaningful assistance and keep users safe in such devices while allowing them the freedom to maneuver freely? We looked for a paradigm for allocating control between the user and the machine that would provide maximal flexibility and yet interfere when necessary. And so here we propose a shared control scheme based on filtering, where at each time instance we assess the user's intent and react in one of 3 ways: accepting the user's action if deemed constructive to the overall task, or if not, rejecting it, allowing failure during training, or replacing it with a controller action, guaranteeing safety during assistance. In our study, we particularly focus on the criterion used for evaluating user input. We employed the mode insertion gradient, a tool from hybrid control theory that allows us to assess the impact of a current action on the impact of on the evolution of the joint human-robot system over time. Existing solutions either blend user and controller actions, leading to a loss of transparency, or they filter user inputs based on a direct comparison with controller actions, sometimes limiting the user's approach to a task simply because it doesn't align with the controller strategy. We created the MIG filter with 3 objectives in mind: that it would be skill sensitive, that it would accelerate training through robotic feedback, and that it would guarantee safety during assistance. To validate these 3 hypotheses, we set up a human subject study. In that study, we recruited 28 healthy volunteers to attempt the task of inverting and balancing a simulated cart pendulum system using this upper limb robotic platform. Each participant completed 3 sets of 30 attempts at the task. In set 1 and 3, they received no feedback, allowing us to gauge participants' skill level. In set 2, they practiced the task with or without feedback, depending on their randomly assigned group, training, or control. We were looking to see whether the better a participant was at a task, the less the controller intervened. And that was indeed the case. In simulation, for a perfect user, the controller did not intervene at all. For Gaussian noise input, the controller intervened about 50% of the time, which makes sense for this simple one-dimensional task. In experimental data, the trend was similar. There was a low but significant correlation between participant skill level, as estimated from task-specific performance metrics in unassisted trials, and the rate of controller intervention during assistance. Secondly, we observed a significant training impact. There was more improvement among participants in the training group than in the control group, across all 4 of the assessed performance metrics, including balance time in the unstable equilibrium. And lastly, we employed the shared control paradigm for assistance for a simulated slip hopper. Note that even for noise input, the hopper doesn't fall. The center of mass is close to its safe trajectory, while only the foot is allowed to make these small random motions. For a simulated unskilled hopper that on its own falls at second 3, as you see here, the controller was able to keep it upright with only 40% intervention. And for a simulated skilled hopper, the controller allowed the hopper to change speed and direction, interfering minimally and exhibiting flexibility that we would expect to see in an assistive device. So given these results, the MIG criterion shows promise to be a valuable assessment tool in shared controlled scenarios. We've shown that it can provide feedback and support to the user, remaining transparent when possible, and interfering when necessary. Thank you.
Okay. Close this. All right, next up we have Lauro Pinto, who's going to talk to us about Asymmetric Actor Critic.
Hi, I'm Errol, and I'll be talking to you about our work on Asymmetric Actor Critic and show how we can use this to learn image-based policies faster. So recently, there has been this growing interest in using reinforcement learning for robotics. This interest has stemmed from the recent successes of RL in challenging tasks like the Atari games, the game of Go, and even real-world robotic grasping of objects. But there still exist several challenges for RL in robotics. The first is the complexity of learnable tasks. And the next is how well do these RL algorithms transfer into the real world. So what happens if you just take a model-free RL algorithm and run it on a real system? So we see that it transfers well into the real world. However, real robots are slow, which means that these data-hungry algorithms will not have enough of data points to work on really complex tasks. So to get more data, what we can do is we can have a simulator version of the robot. And now we can have enough of data to learn complex tasks. But then when we want to transfer these state-based policies in a simulator back into the real world, we now need to do state estimation, which is hard. So instead of that, what we can do is we can learn a policy entirely on rendered observations in the simulator, as shown in these works here. This allows you to transfer well, but now you have to learn an image-based policy, which is often slow and hard to learn. So in Asymmetric Actor Critic, what we do is that we learn an image-based policy, which allows you to transfer well into the real world. But we also use the underlying states available in our simulator to accelerate the learning for our image-based policies. So Asymmetric Actor Critic is based on the Actor Critic architecture, where you have an actor which takes in observations as input and outputs actions, actions which can make the agent go towards its goal. And to do this, we also learn a critic, which again takes in observation as input and evaluates the performance of our policy. Now, during most of the Actor Critic learning, this learned critique is used to provide updates for the parameters of the actor to make the actor perform better. So we note that for image-based policies, we need to have images as input into the actor. But do we really need images as input into the critique? So because we have a simulator, what we can do is that we have access to the underlying full state of the environment, and we can directly use this as input into the critique. This is called Asymmetric Actor Critic, and we show that this makes the critique learn much faster. And because it learns faster, it provides much better updates to the actor. Note that during test time, we only need to use this image-based actor, while the critique is used only in the training phase. So we can see that for even like very simple examples, like the particle environment over here, if you use a symmetric version of Actor Critic, it doesn't do very well, which is at the bottom there. But if you start using Asymmetric Actor Critic, it starts performing much better. We also show that we can also use some sort of state-based experts and do imitation learning from the state-based experts, which is shown in the dotted line. And because the particle environment is a very easy environment, this works really well here. So now let's look at a more harder task, like the fetch pick example over here. So again, Asymmetric Actor Critic works much better than the Symmetric Actor Critic. But more interestingly, we also do much better than the imitation learning baseline from state-based experts. So something we really care about is also transferring these RL policies back into the real world. But we note that the images that we see in the simulator on the left is very different from the images that you see in the real world. So for this, we employ a technique called domain randomization, where we randomize the lighting and textures and viewpoints in the simulator. And this allows us to transfer our policies into the real world. So in our experiments, we have 3 different robotic tasks. The first one is the fetch pick task. Note that it's able to do this without seeing any real-world data in the training phase. So this is an example of a robot pushing this object forward. So if you have any more questions, feel free to ask me at the end of the session or during our poster session. Thank you.
Okay. All right, next up we have Alice Ratner, who's going to tell us about simplifying reward design. Sorry.
All right. Hello, my name is Alice Ratner, and I'm a student at the University of California, Berkeley. But before coming to Berkeley, I worked on planning for autonomous vehicles in industry. And what I found one of the challenges here was actually designing or specifying a reward or cost function that led to good behavior for the vehicle. And one of the reasons why this is challenging is actually because the vehicle needs to operate across a wide variety of different conditions, so different weather conditions, traffic conditions, and so on. And it needs to operate across many complex scenarios, such as the intersections we have here in Pittsburgh. And it's very challenging to find one reward or cost function that leads to good behavior across all of these different scenarios. Now, this is also a problem in manipulation. In our lab at Berkeley, we have a 7-degree of freedom arm, and this arm is used to complete a series of manipulation tasks. And so in order to do that, we need to solve some motion planning problems. So the task here is to plan from some start configuration, shown here, to some goal, while optimizing some reward or cost function. And even for a simple task like this, it can be very difficult to correctly specify and correctly encode the right trade-offs in this reward or cost function. So in this case, we may care about distance from the end effector of the robot to the human, to different parts on the human, as well as to the vase on the table or the table itself. Now, as a reward designer or as the engineer, we implicitly know what these trade-offs should be and what this reward function should be. And the reason for that is because we can identify what the right trajectory that we want to see is, and therefore, even if we can't immediately write down what that reward function should be. So the sliders here represent how an engineer might go about tuning these trade-offs. So in practice, what you'll do is you'll tune these trade-offs until you find that the robot exhibits good behavior under that reward function on the environment that you're considering. So we want this reward function to generalize to new environments. So what we typically do is we first select a set of representative environments, and then we'll tune the reward function, tune these parameters of the reward function until we see good or the desired behavior on all of these environments. And then we can use that resulting reward function to plan in new environments. Now, in practice, though, this can be quite difficult. And the reason is it's very difficult to get the right trade-offs across all environments simultaneously. And what ends up happening is you'll get the right trade-offs on one environment, and that might break another environment, and so on. And so it can be very frustrating. And in fact, this is the key challenge in reward specification, reward design, the fact that it's difficult to find just one reward or cost function that leads to good behavior across all environments simultaneously. So what if we didn't have to do that? What if instead the designer could specify a different reward function for each environment rather than one reward function that needs to work across all environments simultaneously? Well, this would greatly simplify the reward design process, because instead of having to specify one reward function that works across all environments simultaneously, we could instead enable the designer to specify a separate reward function on each environment at a time. But then the question becomes, how do we combine these reward functions to generalize to new environments? Well, while none of these reward functions are identically the kind of underlying true reward that we want, they all hold a lot of information about that underlying true reward. So what we can do is we can take them to be observations of this underlying true reward, and then we can use Bayesian inference to compute a posterior over what that true reward is, which we can then take and use to plan on new environments and generalize those new environments. Now, of course, in order to do that, we need to define some observation model. And in this work, what we do is we model the reward designer as choosing a reward function that leads to a trajectory in the training environment that achieves high true reward under R. So we tested this out. And in practice, what we found is that participants found it found our new framework faster to use. They found it easier to use as well. And the resulting reward functions generalize better to new environments. So what we've done here is we've effectively simplified the reward design process by allowing designers to specify a separate reward function for each environment rather than one reward function that must work across all environments simultaneously. And what this has effectively done is to remove some of the burden on the engineer or the reward designer, instead shift that burden onto the robot to infer this common reward function that can generalize to new environments. Thank you.
Okay, our last speaker is Nakul Gopalan. Give me a second. Okay, go ahead.
Good afternoon. I'm Nakul, and I'm here to present our work on sequence-to-sequence language grounding of non-Markovian task specifications. So imagine you're being driven by a self-driving car along a cliffside, and you want to tell your self-driving car to drive away from the cliffside so that you drive safely. Now, this command that you've given your self-driving car is not really Markovian. It doesn't just apply to one terminal state. You don't just want to be safe in one state. You want to be safe all along the trajectory, which makes this command non-Markovian. And such commands are everywhere. For example, in a house environment, you might ask your robot to first clean the bedroom and then clean the kitchen. Again, this task specification is not really applying to one terminal state, but along the entire trajectory. So in this work, we try to target language grounding to non-Markovian task specifications and then plan over them, instead of just applying to a goal condition or an action sequence. For this, we use a representation which is called linear temporal logic. Linear temporal logic allows us operators like finally proposition P, which means that the proposition P is true at a particular time step along the trajectory, or globally P, which tells us that the proposition P is true along all time steps, or next P, which tells us that the proposition P has to be true in the next time step, or P until Q, which tells us that the proposition P needs to be true until Q. With these operators, we can now say things like go to the yellow, avoid the cliffside, would then become globally never be in states that are cliffsides, or go through the bedroom to the kitchen would look like eventually be in the bedroom, and then eventually after that be in the kitchen. Now we have sort of reduced this problem to, we have some natural language commands, we translate them into the LTL expressions, and then we plan over those LTL expressions with a planner. Previous works that looked at this tried to ground natural language to either some goal specifications or just actions directly. There was some work that looked to ground natural language to LTL specifications, but they had a really small corpus, and they designed the grammar on this corpus. What we looked to do was to do this directly with a large corpus and not design any grammar at all. So we tested our method on two domains. One was a mobile manipulator domain called cleanup, and the other one was a simulated pick-and-place domain. We modeled both of these tasks with Markov decision processes to deal with stochasticity, and we used proposition functions like in the blue room to test particular states of the world to see if the agent is actually in the blue room. So once we have this environment MDP, we then collected data on these MDPs on Amazon Mechanical Turk. We showed people images like this and expected them to give us commands like, go to the green room through the blue room. We then annotated these commands with LTL expressions. Hence, the problem then reduces to translating natural language commands, which are in English, to these LTL expressions. And we use neural sequence-to-sequence methods to do this translation. For doing this translation, we actually need alignment models which tell us how well does an input word at position I match with an output word at position Q. The LTL expressions is a really rigid language. It's symbolic. So we developed our own encoder-agnostic attention mechanism that allowed us to generalize to unseen tasks in the LTL space when given novel natural language commands. So once we have our LTL expression, we then used an off-the-shelf probabilistic planner to solve our LTL expression. This planner was geometric LTL. geometric LTL basically takes in our LTL command, converts it into a specification MDP, which generates a crossed MDP with the environment MDP, over which we can actually plan and generate trajectories real time. So as far as results goes, we tested our method with basic sequence-to-sequence methods with alignment models, and we see that with five-fold cross-validation, where the methods have seen all the possible LTL tasks, our method does as well as all the other methods. However, our method generalizes better to unseen tasks, which is the red curve, where our method generalizes just a little bit better than the other tasks. This problem is still open. We then use our pipeline to plan real time on the robot. The video is available in the paper. The command that we gave was go to the blue room to the yellow room, and the robot was able to plan this real time. So we presented a technique to ground non-Markovian task specifications. We demonstrated this technique in simulation and on a robot platform. We collected a large publicly available data set, and we presented an attention mechanism that allows us to generalize better when the target language is rigid. I'd be happy to answer any questions at the poster session.
Can I get the three other speakers back? Okay. Okay, awesome. Time for questions. So who has any burning questions? One over there. Guy with the blue. Blue mic.
Ladell, this is a question for you. So in the asymmetric actor critic, you're using the states to learn the critic and you say that helps the critic learn faster. Is this only true, or is this only really necessary in the deterministic policy case where you're differentiating through your critic to update your actor, or say in the stochastic policy case when you can apply stochastic policy gradients, could you use a Monte Carlo style update where you don't need a critic network at all? Have you observed this being better than that as well?
Well, in my observation, doing policy gradients without this method is just slow. So if you want to learn faster, you do need like actor critic like architectures, at least in my observations. So yeah.
Okay, thanks. Guy with the green mic, green box.
For Nakul. So interesting talk. I have a question. So you're modeling this as a sequence-to-sequence learning problem, but LTL doesn't have the order doesn't matter. And I was just wondering if you found there's a paper by Oriel from I think 2015 where they look at in cases where it's not really a sequential task, the way that you present the data to the model, both input and output, affects the model that's learned. So I was just wondering if you found this. You say alternating the order in your training data.
Oh, you mean alternate
the output order?
The output order.
Because your modeling is sequence to sequence, right? But the output really isn't a sequence.
What we did was actually looked at some generalization where we tried to generate synthetic data and train the output model without presenting any input. So the output model, we generated some synthetic data, trained the output decoder side. So we weren't really dependent on, we learned a transition model of the decoding model independent of the input model.
Okay.
Which sort of allows us to generalize better. I'm not sure if I'm answering your question directly, though.
We can take it offline.
OK, thanks.
Great. OK, guy with the blue mic.
Hello. This is for the third speaker. Yeah, so you talked about generalizing the cost functions to different environments, but how do you parameterize an environment? Is it like, and without actually exploring the environment, you wouldn't really know what cost function to use until you explored it completely. So how do you solve that?
Yeah, in this work, we assume that we have full observability in the environment. So we basically have the ability to simulate or forward simulate the environment. Is that what you're asking? Or?
Yeah, that's what I was asking. Thanks.
Any more questions? OK, guy with the green mic.
Thank you. I have a question for the first speaker. I was wondering, you're doing your control based off of some expected objective and the knowledge of that objective. what's the stability when the objective is not clearly understood or known?
So we've defined our objectives in as limited scope as possible to guarantee success. And then the stability depends on the stability on the controller if you're using the filter in an assistance mode where you're replacing the actions with the controller actions.
Okay, we have time for one more quick question. Does anybody want to ask one last question? No? Okay, I'll where? Ah, great. Okay. Blue mic.
Assume that you have several environments from a designer and that you can kind of embed them into one reward. So what is your intuition behind the belief that even if for a human there are several rewards for each environment, the robot may learn only one that can embed it, and it's going to generalize to new environments?
Yeah, so actually what we do is we don't just learn one, or we don't infer just one reward, we actually infer a sort of belief over these rewards. So for example, if under the given examples and provided or designed reward functions, if it turns out that there are multiple reward functions that are equally likely given what we've seen, then that belief distribution kind of encodes that information.
Okay. Great. Thank you all for your questions. Let's thank our speakers once again.